My name is René Williams. I am assistant professor at the Molecular Photonics group at the University of Amsterdam. And today we will discuss the Exciplex. We will talk about charge transfer absorption, charge transfer emission, also called Exciplex emission, in molecular complexes. And we will make a connection to geminate and non-geminate radiative charge recombination in semiconductor materials. The discovery of the excited state dimer of Pyrene, the excimer. As a result, people also started studying the interaction of electron donating molecules with Pyrene, and that led to the Exciplex, charge transfer complexes. They are exemplified by perylene, pyrene, and fullerenes, especially with aniline donor molecules. From the excimer of Pyrene, we go to the Exciplex, to complexes, but we also talk about solids. We will even talk about perovskites. Everything you know all now about the excimer of Pyrene. You have an excited state molecule, it meets a molecule in the ground state, they can form this excimer, and it shows excimer emission. It is the excited state dimer, and they do not interact in the ground state. The Exciplex showed very, very similar emission, and that is why they called it like that. So it's an excited state complex. So here you see Pyrene, the excited state. It meets a dialkyl aniline, and it forms this charge transfer state, a radical anion and a radical cation of the donor. If DNA are the same, then we have the excimer, and you have seen this before. We have local emission of, for instance, pyrene, but if they meet each other in the excited state, they can form this excimer, this dimer, and we can represent it like this, and it gives this special emission, this broad structureless redshifted emission. It is a very nice fingerprint of this interaction. If there is a donor and acceptor, you can have this same emission, but if you take a very, very close look, then you actually can measure that there is some interaction in the ground state. We have an emission that's very much like an excimer, but there is some interaction in the ground state. So here we see that in the ground state, there can be a small minimum, but we can have the same Exciplex type emission. We can have a contact radical ion pair. So we create, by electron transfer from the donor to acceptor, we create this radical ion pair, and it can emit, but we can also measure its absorption. This is work from 1972, just some absorption spectra. So here you see the absorption spectrum of pyrene with this forbidden transition. It is a very, very high concentration. This is the donor by itself, but then if you start mixing them together, you see that there's extra absorption band below the normal absorption, but also here on the red edge. So this implies that there's already interaction in the ground state. We can call this charge transfer absorption because you have a direct optical transition into this charge transfer state. Here we see a better donor-acceptor pair. That's called tetracyanoanthracene. So it's a very good electron acceptor. It is a very electron-poor species. This here is pentametal benzene. It's more electron rich. It's a good donor. If you take the absorption spectrum of only the anthracene, you see these sharp peaks. If you keep on adding electron donor, you see that on the red edge, where the anthracene does not absorb light, you see an extra absorption band. And that is correlated to the concentration of this donor. So this is a direct optical transition into the charge transfer state. So it's a charge transfer absorption band. There is not only charge transfer emission, like the excimer of pyrene, but there's also charge transfer absorption. And so this is, again, one of these anthracene molecules. Here you have this charge transfer absorption band on the red edge. Here it is enhanced. And this here is the charge transfer emission. Yeah, so the charge transfer emission, charge transfer complex of these molecules. If you represent these states with potential energy curves, then this is the ground state, this is the charge transfer state. Now the energy difference between the charge transfer absorption and the charge transfer emission, that's actually related to the energetics. It is the internal reorganization energy. The maximum of this band, which is estimated to be here, and the maximum of the charge transfer emission, or the Exciplex emission, this energy difference, so if you convert the energy difference from wavelength to electron volts, then this is 2 times the internal reorganization energy. So it is the energy that is needed to distort one state into the equilibrium geometry of the other. So that gives you information on the energetics. And this here all is in cyclohexane, so that's a non-polar solvent, where the solvent reorganization is negligible. So in that way, the Exciplex is different because it has charge transfer absorption, charge transfer emission, and the charge transfer emission, we can also call it Exciplex type emission. That is more appropriate. Now, one of the first combinations that was actually studied is perylene and dimethyl aniline. That was by Baines and Knibbe. And they saw that in a polar solvent, you get free ions, so you can get solvated ions. Okay, these molecules, they collide. One of them is in the excited state. You have charge separation, and then the ions can separate in a polar solvent. Of course, at a certain point, they will meet again and recombine, but the solvated ions, they can live quite long. But in non-polar solvents, these molecules try to stick together because the solvent does not help them energetically to go apart. So there you can see the Exciplex emission. The Exciplex emission of perylene and dimethyl aniline was also one of the first. And interestingly, if you have the excited state of the perylene, dimethyl aniline is the quencher that makes the local emission disappear because of the electron transfer process. Okay, this is like an encounter complex where the molecules meet. Here we have the charge separation. And here we can have the diffusion of the ions that separate into the solvated ions. But in this case, this charge transfer state, it can recombine onto a triplet state, a triplet of the perylene. So that's quite special. And in non-polar solvents, but you see that there's a resonance structure between the excited state and the charge transfer state, because they are, of course, in a non-polar solvent, they are more close, so there can be more interaction. But also here, this state, it can form a triplet, which is quite interesting. But importantly, it shows this charge transfer emission, this Exciplex emission. Perylene dimethyl aniline system. This is all early work, but they already have stated that there can happen in this Exciplex type state, you can have intersystem crossing. Now that is very intriguing to me, but it also shows that the lifetime of the Exciplex emission is like 126 nanoseconds. So it's very long in a non-polar solvent because you're still high in energy and there's this mixing with this forbidden local state. So in that way, you can get a lot of information about the interaction between these two molecules in the excited state complex. People have started connecting covalently these kind of molecules together. And this is one of them only a few years later. So you see 81. And they show that in 40 picoseconds, this molecule in the charge transfer state converts to the triplet. The statement that you just saw about the intersystem crossing, in this molecule in which the units are like almost orthogonal, you have the triplet here at 415. This is absorption of the excited state. And at 415, the triplet grows in, and it grows in very rapidly. So this gives very fast decay of the Exciplex state or the charge transfer state into the triplet. So very special. This here is a very, very short space, right? These molecules are very close by, only one CH2 group in between. Here we have 3 of these groups in between, and then you can have more information about the conformational flexibility. You can have a compact Exciplex, and in this case, it takes slow, it takes a longer time. You can have an extended Exciplex, which can fold, or you can have a direct fast formation of this loose Exciplex. So these are all interaction between the molecules that represent the first Exciplexes, but now they are covalently connected. So you restrict their movements. So the top one, this molecule has to fold before you can have the charge separation. You have to fold the molecule because energetically, this state in N-hexane is, of course, a little bit higher. A polar solvent will lower the charge transfer state because the charge transfer state is ionic. So the first one, The molecules have to first fold, and then you can have for the exciplex formation. That's why it's slow. The folding is slower. The second one, to have the charge separation, because the charge state is a little bit lower, and then you have electrostatic interactions. Charged units, they attract each other. But if the solvent is very polar, you can have direct formation of these charge separated states, but now the solvent, it stabilizes the separated ions. So there's very strong solvent effects that either play with the energetics, they make the energetics higher or lower, and also the solvation of the ions. So these are aspects in the charge transfer complexes or the exciplexes that are formed. So you excite the system, it has to fold, and in the folded conformation, you can have the exciplex formed, which shows then this special emission. So we go from the excited state of the dimer to the excited state of the complexes, and we can make them connected. If we connect them, we have more control. We're not relying then on diffusional processes. It also gives us a tool to influence the properties. So here you see that the classical combination, pyrene and dimethyl aniline, they have been coupled together with Sonogashira coupling. They've inserted a triple bond. So there's a triple bond between these two units. So you fix them, but it also is very important for the electronic interaction that also changes. Now, the interesting thing is the emission, it is very dependent on the solvent polarity. So you go from a blue emission in cyclohexane to a yellow emission in acetonitrile. And there are molecules that have an even larger shift. They go from blue to red. And this is charge transfer emission. You have a local excited state, you have a charge transfer state, and it emits to the ground state, but this level, can become lower and lower depending on the polarity of the environment. This molecule tells you something about the environment. So here we see some spectra. This is just an example of a molecular probe. So these sharp peaks with vibrational fine structure, that is local emission. In very non-polar solvents, this charge transfer state is not accessible. There's not enough driving force. But in these more polar solvents, you create the charge transfer state, you create an exciplex type species, and the emission is now very sensitive to the environment. This is in benzene, and then you go more and more polar to acetonitrile. This molecule is a solvent polarity probe. It tells you something about its environment, so you can use it as a molecular spy, as a molecular probe. And you're using exciplex emission. The color depends on the solvent polarity. There are also similar molecules like dimethylamino nitrostilbene. They're actually used as a Q monitor. So you can monitor the polymerization or how rigid a polymer becomes, how viscous it becomes. As a function of polymerization degree, the emission color changes. In that way, you have heard of the Ham effect of pyrene. There was this slight change of vibrational fine structure with solvent polarity. Now we have a huge emission shift, and you can even see the color by eye. So if you just put it under a UV lamp, you can see, okay, the polymer is not ready, or it is more polymerized, or the environment of the molecule is polar or non-polar. So it is polarity, but also rigidity. So that makes exciplex type emission a very useful tool to probe environments. We have seen very nice examples of exciplex emission, charge transfer emission. This is an example of charge transfer absorption, which is more intense than you have seen before. This here is the absorption spectrum of C60. It has a very low molar absorption coefficient. I think it's 300 here in the visible. If you dissolve it in diethyl aniline, in the strong donor, you see that the absorption changes enormously. It becomes much more intense, and it's also redshifts. So this is all charge transfer absorption. If you plot the intensity here as a function of the concentration of the donor, then you see that it increases. So there's a relation between the concentration and the charge transfer absorption. It shows you all the intermediate steps with intermediate concentrations. So this is the C60. This is C60 in pure dimethyl aniline. So there's a very, very strong direct optical transition to the charge transfer state. And in this paper here from Mr. Hochstrasser, they also probe that interaction with very, very fast spectroscopy with femtoseconds. The change of the absorption spectrum, so it is the charge transfer absorptions from very similar molecules, also for C60, but this example is actually for C70. You see that it can also show this Exciplex emission. So in a non-polar solvent, if you add in diethyl aniline into C70 solution, so you see that the emission is first for C70 itself is like this, let's say the lowest curve with this vibrational fine structure. And then if you add in a higher and higher concentration of the donor, you see this red-shifted structural band arise. So it tells you there's charge separation. This charge transfer state, it can emit, it gives a radiative process, it gives off emission, and it tells you something about the system. It gives you information. From the excimer came the Exciplex, and the Exciplex, well, maybe it's better to call it a charge transfer absorption complex, because it gives charge transfer absorption. It also gives charge transfer emission. It is important. So people call it charge transfer emission, but it's charge recombination. The state goes back to the ground state, and the electron goes back from the reduced acceptor to the oxidized donor. So it is a charge recombination. So that implies that this emission, this special emission of the Exciplex of Pyrene and these C60 aniline systems, it is what we call radiative charge recombination. So it is charge recombination, the charges recombine, and it's a radiative process that implies it is emission. This is a term that you indeed encounter in the perovskite field. This is a paper from Strangs, Cambridge. So this is a very interesting paper about what they call non-radiative losses. Non-radiative processes, they are a loss channel in perovskite solar cell materials. And that implies that an optimal solar cell material like gallium arsenide or silicon or things like that, they should give only radiative charge recombination. So they should give off an emission. It looks a little bit different from the Exciplex emission, but it's the same principle. It's the same process. So if you have a semiconductor, you shine light on it, or you inject charges with electricity, then there should come off emission. And this emission, if it is very efficient, that implies that there's no non-radiative losses. So that connects the excimer, the Exciplex, to solar cell materials, even to perovskites. They need a high radiative efficiency, and that's a prerequisite for the theoretical limit. So that's also in the so-called Shockley-Queisser limit. The only decay should be radiative. Exciplex emission is basically charge transfer emission. It is the same. It is a radiative charge recombination process. But now we can wonder, can we make a distinction between geminate and non-geminate? And now I'm going to ask you to say something. Can anybody comment on geminate or non-geminate processes? Do you know what that means?
I have no clue what that means.
Geminate, it is related to Gemini. And you know what Gemini are because they are twins. Charges, if they are born together, just like Gemini, just like twins, they are bound together. They come from the same photon. So if you have, like for instance, this pyrene donor molecule, if you excite it, you have the donor acceptor in solution. The charges cannot go anywhere, so they can only recombine back on the same molecule. Geminate charge recombination implies that the charges were born together, they were made together. Now, what about the non-geminate charge recombination? That actually implies that these charges, they don't know each other before. And that can also happen. If you take a material and you inject a positive charge and a negative charge, they were not born together. They just come from electricity, from electrodes. But if they meet on the molecule, you can have emission. This is the principle of a light emitting diode. If you have a solid state semiconductor, You shine light on it, you create charges. The charges can move around the material until they meet another charge. So this is also non-geminate charge recombination. So it's a very important distinction. And here are some papers and some data about organic solar cell materials and Exciplex type emission, charge transfer emission. This here from 2012, that's actually a review from Maria Loy from Groningen. These other papers are, I think, from the data itself. On the left, we see a polymer, FHDTBT, it's called, don't ask me why. And it's mixed with this PCBM, with the fullerene. It is photoluminescent, so they excite the films. They have a different ratio of PCBM added in. This is PCBM itself. This is the polymer itself. So if you add in more and more PCBM at 33 and also at 66% of PCBM, you see a red-shifted emission band. Now this is charge transfer emission. It's Exciplex emission in a thin film in a material that is used as an organic solar cell. It implies that in this film, you create an exciton, you have charge separation, but for certain conditions, certain combinations, they can give radiative charge recombination. So it tells you something about the lifetime of this charge transfer state. It gives you extra information to probe it. And that is actually not very common for these films, but there are examples. But the other one, that is electroluminescence. This is geminate charge recombination. These solar cells do not work very well with these materials, with these specific materials. So because the charges partly recombine directly, giving emission. But what about this combination? So it's a different polymer. It is the same fullerene acceptor. Here we have MDMO PPV, so it's phenylenediamine system. And here you inject charges, a positive charge and a negative charge. They meet, and you see emission from the charge transfer states. So this here is certainly non-geminate charge recombination. So it's the same structureless emission band, just like the Exciplex of pyrene dimethyl aniline. It is due to charge recombination, but in this case, these charges, they were injected with electrodes into a film, but it is the same type of emission.